Greetings, CP Physics. The next unit we're going to do is on linear momentum, and this involves collisions and stuff moving and smashing into each other, so it's going to be fun. So first, a little introduction to momentum and then some impulse. And all of you are very impulsive people, so you should already know what impulse is. So momentum has a lot to do with the conservation of energy. It's actually a lot simpler to use than conservation of energy to find velocities like before and after collisions. So we're also going to learn about momentum. We're going to learn about some impulse, conservation of momentum, one-dimensional collisions, and two-dimensional collisions. So just a quick review of the conservation of energy. I'm not going to spend a lot of time on this. Remember, the change in energy is equal to the change in kinetic plus the change in potential. And the change in energy, if it's conserved, is 0. So the total amount of energy in the system is constant, doesn't change. That's why the change in energy is 0. The energy before equals the energy after. So here's all of our different energies right here. Here's our K. Here's our P. Here's our spring potential. And the same on the other side, K, P, spring potential, different color. So we also know that that equals the work. So here's our work guy right here, force times distance. In this case, the force is the frictional force. This would be a non-conservative force if energy isn't conserved, but we're not going to worry about that too much. And the total amount of energy in the system is still constant, but the change in mechanical energy goes into internal energy or heat. So there's still energy is still conserved if there's friction. It's just that energy isn't changed from potential to kinetic, kinetic to potential. There's also heat involved. But don't worry, we're not going to do anything with that guy. And this is what it would look like, just putting that, frictional stuff up here. So linear momentum is a new quantity. It's like force or energy. It's a fundamental quantity. And it's a vector, and that vector is going to point in the same direction the object is moving, the same direction as its velocity. Momentum, which we denote with a lowercase p, little p, of an object of mass m moving with a velocity v, is defined to be the product of the mass and velocity. Pretty simple equation. It's just p equals m times v. And these little arrows, of course, mean that these are vector quantities. Since velocity is a vector quantity, momentum is going to be a vector quantity. They're going to point in the same direction. The terms momentum and linear momentum will be used interchangeably in your text. We're not really going to talk too much about rotational. In fact, I'm having you skip the rotational sections of your book in the momentum chapter. And so, basically, all depends on the momentum as the mass and the velocity of the object. Pretty simple equation. So here's a quick little conceptual thing. Two objects of masses m1 and m2 have equal kinetic energy. How do their magnitudes of their momentum compare? So if they have equal kinetic energy, that means 1/2 m1 velocity 1 squared equals 1/2 m2 velocity 2 squared. We can get rid of those 1/2s. So we're left with m1 v1 over m2 v2 squared. So there's really not enough information to tell because we don't know the masses. And because if this one has a small mass, it's got to have a big velocity to make up for the little guy's mass. Or say m1 is huge and v1 is small. It can have the same kinetic energy, same momentum as a small object going really fast. So you really can't tell right now. So I already said it's a vector quantity. There's its formula, same direction as the velocity. Dimensions of momentum are mass, length, and time. So this comes from the equation right here. So this m, it's a mass unit. So it has dimensions of mass units. Velocity is a length divided by a time. So therefore we get m equals lt, or ml over t for the dimensions. In our case here, it's going to be kilograms, meters, over seconds, which are the SI units. Unfortunately, it doesn't have a pretty unit like a joule or a Newton. You got to leave it as kilograms times meters over seconds. It can also be expressed in component forms. Cut off my y. There should be a y here. Momentum in the x direction equals mass times velocity in the x direction. Momentum in the y direction equals mass times velocity in the y direction. Momentum in the z direction equals momentum, or mass times velocity in the z direction. We aren't going to worry about z's. We don't like 3D stuff. We're only going to be worried about one-dimensional and two-dimensional stuff. So Newton's second law can be used to relate the momentum of an object to the resultant force acting on it. So force equals mass times acceleration, and acceleration equals change in velocity over time, and therefore the change in the mass times velocity, which can be your change in p, over your change in time, is going to equal the net force, which is exactly what I just said right down here. So the change in object momentum divided by the elapsed time equals the constant net force acting on the object. So force equals change in momentum over time. That brings us to impulse. So when a single constant force acts on the object, there's an impulse delivered to the object. Very impulsive people, they like to shop and spend all their money. Another very simple equation, I equals F times delta T. And we use this I with a little bar over it, showing that I is a vector quantity. It's obviously going to be in the same direction as the net force. This equality is true even if the force is not constant. If it's a changing force, you're still going to have an impulse over on this side. Vector quantity, already said, same direction of force. And it's easy to see where we get this. I equals F delta T. So if I just forget about this guy right now, I have F net equals delta P over T. So therefore, I bring my delta T over to this side. So I get delta P equals F delta T, which equals I. So there's a theorem called the impulse momentum theorem, and it states that the impulse acting on a system is equal to the change in momentum of the system. It's basically just what I had on that last page. The impulse equals a change in momentum. And change momentum, since it's a delta there, you do the initial momentum. So this will be your P initial over your, P final minus your P initial. So mass times velocity final will give your momentum final. Mass times velocity initial will give your initial momentum. So here I have a bear and a ball. They're both dropped from the same height. They're going to smash the ground. But the bear, he's going to stay there. The ball, he's going to bounce back up. So if we know that change of momentum equals momentum after minus the momentum before, and there's our little equations for both of those momentums, you pull out that m. So m times velocity after minus velocity before in parentheses. So for this teddy bear, what do you think it's going to be? Since he doesn't have any velocity after, you put a 0 in there. Velocity before is negative, so it's downwards. So his change of momentum is just his momentum, his mass times his velocity as he's going down. For the bouncing ball, on the other hand, it's going to have a little bit bigger, because this time that he has a velocity going up after he bounces, and velocity is negative going down, so we're left with change of momentum is 2mv. Pretty easy stuff. So bumpers on your car deal a lot with impulse and momentum. So in a crash test, a car of mass of about 1,500 kilograms collides with a wall and rebounds, as in this picture. So he's going to the left at 15 meters per second. That's why we have a negative here. He bounces off, going the opposite way at 2.60 meters per second. Now if you bounce off going 15 meters per second, you would probably die. So bumpers are used to lengthen that time that you're in contact with that wall, which decreases the force and therefore the impulse. So I already said what the initial final velocities are, and here's how long the collision lasts for, 0.15 seconds. So we're going to find the impulse delivered to the car, and we're also going to find the size and direction of the force exerted on the car. Where'd that arrow come from? All right, so we find the initial momentum to begin with, 1,500 kilograms times negative 15 meters per second. Multiply that together, you get negative 2.25 times 10 to the 4 kilograms times meters per second. The final momentum, use your final velocity, multiply it together, you get 0.39 times 10 to the 4. Now remember that the impulse is the change in momentum, so we just take this guy minus this guy, and you get this number, 2.64 times 10 to the 4 kilograms times meters per second. So now we're going to find the average force. Pretty easy. Remember, force equals delta t, or sorry, force times delta t equals I, so we got to bring that delta t over here. And therefore we take our impulse, which we found in part A, divided by our time, and you get 1.76 times 10 to the 5 newtons. So as your time gets bigger, your force is going to get smaller. So time goes up, force goes down. So the longer this time is, the less force, and the less chance you have of getting hurt. So that's what bumpers do. They increase this time. Say if we had just a steel plate on the front of our car, this would be a very small number, so this force would be bigger. We'd probably get hurt a lot easier in car crashes. That's why a lot of cars nowadays are designed basically just to crumble whenever they run into something. Like all the fiberglass just smashes together because it increases that time, which decreases the force. Okay, and here's a simple little one. Child bounces a 100-gram super ball on the sidewalk. The velocity of the super ball changes from 10 meters per second downward to 10 meters per second upward. If the contact with the sidewalk is 0.1 seconds, what is the magnitude of the impulse? Remember, the impulse equals the change of momentum, so we got to find the momentum before and after. So mvi is going to be 0.100 kilograms times negative 10 meters per second, which is just going to give us negative 1 kg times m over s. Similarly, mv final, 0.1 kilograms times a positive 10 meters per second. We're going to get positive 1 kg times m over s. Now our impulse is going to be this guy minus this guy, so 1 minus a negative 1, which gives us 2 kg times m over s. You could also use the other handy-dandy little one, just m vf minus vi. So it's going to be 0.1 kgs times 10 minus a negative 10, which is 20. 10 minus negative 10, which is 20. So 20 times 0.1 will also give you 2 kg times m over s. Now we're going to look for the magnitude of the force. So remember, I think I have it printed right there. I do. Remember, I equals F delta T. Solve this guy for F. And also I equals a change in momentum. So we just use our answer from the last one, divided by our time. Pretty simple. 2 kg times m over s, divided by 0.1 seconds. 2 divided by 0.1 is going to give us 20. Kg times m over s divided by s is going to give us kg times m over s squared, which is a newton. So 20 newtons. Pretty simple stuff. Some of the problems get a little trickier, which is why we do them in class instead of doing them for homework. So enjoy.